The last descriptive statistic that I want to demo for you is called confidence intervals. This is going to be the last thing that we talk about before we run actual inferential tests, but it's really important because confidence intervals are what we base our interpretation of the statistical test on. So to do that, I know I'm under analyze, I know I'm under descriptive. I'm going to go to explore data, and under statistics you'll see the default shows a confidence interval of 95%. That's like setting our alpha at 0.05, so I don't need to change anything. So I'm going to scroll down to my math scores, the percent correct students got during a particular year, and I'm going to click OK. This second table really highlights what I want to emphasize here. The first statistic is the mean, and it just simply shows us that on average students got 72.2561% of the questions correct on the math, and the lower bound is not much lower, 71.88, and the upper bound is 72.62. The reason the upper and the lower bound are so close to the actual mean is because we have a sample with over 15,000 students in it. So the analogy I like to give people is to think of your sample like you flipped a coin. Imagine that I only flipped the coin 10 times. And of those 10 times, I got 8 heads and 2 tails. We'd expect 5 heads and 5 tails. But I got 8 heads and 2 tails. Would I conclude that my coin's warped? No, because I only flipped it 10 times. Well, in this case, I flipped the coin 15,496 times. So I'm really confident that the mean that I got of 72.2 actually represents the mean for the entire sample. But the mean for the entire sample with a 95% confidence interval falls between 71.88 and 72.62. That's a confidence interval. More importantly, I'm going to show you how confidence intervals can change and sometimes be misleading. So in this case, I'm going to open up a new database, and I'm going to enter scores for just 10 students. And let's say student 1 got 28% correct on the same math test. Student 2 got 67, 3 and 4 got 75, student 5 got a 98, student 6 got an 88, 75 again for student 7, a 90, a 47, and an 85. Those are my 10 student scores. I can go up to my descriptives again, go to explore, and run a confidence interval of 95% on those. And this time, my average score, my mean score for those 10 students was 72.8. However, I can only be 95% confident, if you will, that the real mean is between 57.7 and 87.9. So why is this important? Obviously, with my sample size of 10, I'm less certain about what the real mean is. So I'm much more unlikely to reject the null hypothesis and conclude some mean difference when I'm not so sure what the mean means. In the case where I had 15,000 students, within a point in each direction, I knew what my mean for the sample was, or for the entire population. So let's say that now we're moving into this realm of accountability. And the goal in the state of Kentucky for all students and for each group of students by race is to score at least a 60% correct to be considered proficient. So I'm in a school and there's not a lot of diversity in the school, and I only have 10 Latino students. And those 10 scores I entered are for the 10 Latino students. Their average score is a 72.8. That's higher than my goal of 60. So I'm not going to be sanctioned for my Latino student performance. But now, let's say the goal goes up to 75% correct for each subgroup of students. Just for these 10 Latino students, who are my only 10 Latino students in the school, they really made a mean of 72.8. And the goal is 75. So I'm going to sanction them, right? No, because the true mean could be as high as 87.9, which is higher than the goal of 75. So when schools and states and so forth created these accountability models, they often used confidence intervals. And now I'm going to give you a more extreme example. Let's say the goal was every subgroup of student had to get 85% correct. Well, this group of 10 Latino students only had a mean of 72.8. Are they identified leading to school sanctions? No, because the actual mean could be somewhere between 87.9 and 57.6. 87.9 is higher than 85. They met their goal, even though, with all sincerity, they're really 13 percentage points below the actual target goal. So when you have really small groups, you only flip the coin 10 times, and let's say, from a positive perspective, I know I only have 10 students. If I'm going to identify them for sanctions for a school, I want to be absolutely certain. That's the justification for confidence intervals. You don't identify someone who's had a 72.8 if the goal is an 80, because the true mean could be above 80. So you're not going to over-identify schools, because you know for low N sizes, there's a lot of error, if you will. On the flip side, I could have drawn this in such a way and entered scores where you could have been 40 points away and still met the goal. So it gives the perception of greater accountability for small N sizes than really exists. And it's very important in the context of accountability. These confidence intervals can be really wide with very small samples, and as the sample size gets larger and larger, the confidence intervals shrink because you flip the coin more times, you measured the test more times, and you're therefore more certain that the mean is representative of your sample.